Good morning, everyone. It's my great pleasure to be here and present and participate in this workshop on this very special occasion of Mark's 68th birthday. So I'll be talking about some novel mechanisms for detecting early warning signals of regime shifts in a predator-prey model. So this is a joint work with Dr. Saikat Thakur from Auburn University. So as we all know, regime shifts are observed in many ecosystems. Some classic examples include clear water lakes switching from, shallow water lakes switching from clear water state to turbid state dominated with microalgae, or we could have coral reefs transitioning from coral dominated state to microalgal dominated state in the Caribbeans. In terrestrial ecosystems, we see a collapse of population cycles of whales in northern Sweden. And in some ecosystems, we can even have extinction. So one example of such is extinction of Steller's sea cow, which was found extinct within 27 years of its discovery. So regime shifts are very important. They're usually hard to detect. And usually regime shifts are associated with slow changes in environmental parameters, which could push the system over its tipping point. And the common mechanisms associated with regime shifts are B-tipping or bifurcation-induced tipping, though there could be other tipping mechanisms like rate-induced or noise-induced tippings. And in the framework of B-tipping, the statistical metrics such as rise in autocorrelation or rise in variance are used as early warning signals to predict the approach to the tipping point. Okay, but we could also view regime shifts through the lens of transient dynamics. More precisely, we can view that an ecosystem is in a transient state and that can persist for a very long period of time for several generations, and then it shifts to the other state. And so one can view regime shifts by, or understand regime shifts by looking at underlying mechanisms or looking at mechanisms underlying the transient dynamics. And this approach has been suggested by Alan Hastings, Andrew Morozov, and many other leading experts in this field. And this is the approach we'll be taking in today's talk. So without any delay, I'll be discussing a predator-prey model where we have three species. We have two predators, Y and Z, predating for the same species X. We assume that X grows logistically given by this first term, and then the predation of X by Y and Z are given by these two terms where we are assuming Halling type 2 functional responses. The consumption of X leads to the growth of Y and Z given by these terms, and then we have the natural death of Y and Z given by these two terms. Further, we take into account interference competition between Y and Z given by these terms. And then further, we have intraspecific competition in Z given by this last term over here. A little bit of background about this model. So in absence of intraspecific or interference competition, the model was studied in 1970s and 80s to demonstrate the effect of competitive exclusion, which just states that two consumers relying exclusively on a single resource cannot coexist in an equilibrium state. And so the only possible coexistence state in this scenario is via large amplitude limit cycles. Now, when we take intraspecific competition into account, so when m is not equal to 0, then it turns out that the three species can coexist in an equilibrium state, which means that density-dependent mortality can prevent competitive exclusion. We further extended this model by taking timescale separation into account, and then use methods from geometric singular perturbation theory to study complex oscillatory patterns that could arise in this scenario. So again, going back to the model, we non-dimensionalize our system and look at our non-dimensionalized model given by system 2 over here. So we have this epsilon, which measures the ratio of the growth rate of the predator to the prey. And we are assuming that our prey reproduces at a much faster rate than its predators, which is going to make epsilon to be a number much smaller than 1. So this is our singular parameter, and that brings in timescale separation into our model. And that's a natural assumption to make, because in real ecosystems, if you think about the prey species to be rodents or insects, they reproduce at a much faster rate than their predators. So we are going to hold all our constants, parameters to be constant, except for h, which will be a bifurcation parameter. And we are going to assume these, we are going to assume that our parameters satisfy these conditions. So since this is a slow-fast system with x being our fast variable and y and z being our slow variables, we'll be using ideas from a slow-fast system to understand the dynamics of this model. So a little bit of geometry, the underlying geometry. So the set of equilibrium points of the fast systems in the singular limit, if you look at the set of equilibrium points of the fast system, that forms a critical manifold. And in our case, our critical manifold consists of two pieces. One is the surface S, and the other one is the plane x equals 0, which we denote by pi. The manifold could be attracting or repelling based on the signs of the eigenvalues of the linearized problem. And then we have our fast flow denoted by double arrows over here. So the fast flow is either directed towards or away from the critical manifold. And the slow flow is restricted to a critical manifold, which is denoted here by a single arrow. The two pieces of a critical manifold, they meet along this line, which we denote by TC, and that's where transcritical bifurcation of the fast system happens. And then this curve F, that's the fold curve where we have saddle node bifurcation of the fast system. So this is our underlying geometry in the singular limit. Now we could get interesting dynamics near the fold curve if there are certain points called Carnot points or folded node singularities. So these are isolated set of points on the fold curve which allow the slow flow to cross the fold curve from the attracting side to the repelling side of the manifold. And these points can induce local oscillations in the system as we see here. And if there is a global return mechanism that brings us to something called the singular funnel, which is a region in the attracting part of the critical manifold, then we could get oscillation patterns which are mixture of a small amplitude and large amplitude oscillations, and such oscillations are called mixed mode oscillations. So in this work we will be actually looking at these kind of complex oscillatory patterns called mixed mode oscillations. And then furthermore, if we have the equilibrium point, which I'm denoting by E star, that lies in the vicinity of the fold curve, and if it happens to cross the fold curve and merge with this folded singularity in the singular limit, then such a point is called a singular Hopf point. So in the protort system, in an epsilon distance away from the singular Hopf point, the full system would undergo a Hopf bifurcation, and we call that Hopf bifurcation to be singular Hopf bifurcation, as it is characterized by singular parts of the singular nature of the imaginary parts of the eigenvalues. In other words, the imagined parts of the eigenvalues would go to infinity as epsilon goes to 0. So we'll be looking at a parameter regime where we have a singular Hopf bifurcation in our system. And we'll be looking at two scenarios. In the first scenario, we'll assume that our singular Hopf bifurcation is supercritical. That's the scenario 1. And in scenario 2, where our Hopf bifurcation is subcritical. So when we have a supercritical Hopf bifurcation, we have a stable limit cycle born out of the Hopf bifurcation, which I've shown here in blue. And we have transient dynamics in the form of mixed mode oscillations in the system before the system approaches to its asymptotics, to the Hopf limit, to the Hopf cycle. And these transients can persist for a very long time, depending on the initial condition and on the parameter values. And if we take a close look at the time series, then we see here that the local oscillations before the system spikes or before it approaches the small amplitude cycle, the local dynamics appear very similar. So you really cannot tell the difference that what is going to happen next. And so the questions are, can we detect early warning signals of spike? And can we predict the timing of the regime shift? So these are the two questions we'll try to answer in scenario 1. In scenario 2, where we have a subcritical Hopf bifurcation, what happens here, we have our coexistence equilibrium point, which I'm denoting by E star, that undergoes a subcritical Hopf bifurcation, which I've denoted by H2. It's a saddle cycle, and then it stabilizes to a periodic limit cycle at a torus bifurcation, which we are denoted here in green. And the system exhibits bistability between this periodic attractor and this another attractor in the system, which is the boundary equilibrium state, where the species Y is absent. So we have bistability between our periodic attractor and our point attractor. And if you look at the phase space over here, then depending on the initial conditions, as we start close to our E star, either we approach the periodic attractor like this, or we could go to the boundary equilibrium state. And so a little bit of perturbation can bring us from the basin of attraction of this periodic attractor to the basin of attraction to the other attractor. And so the question here is, can we determine early warning signals of extinction of Y? And so that's the second question we'll be trying to answer in scenario 2. All right, so first let's consider scenario 1, where we have a supercritical Hopf bifurcation of our coexistence equilibrium state. Here is a small limit cycle that is born, and we have transients in the form of mixed mode oscillations. The equilibrium point is a saddle focus with one-dimensional stable manifold and two-dimensional unstable manifold. So to understand what is going on, we will be doing a local analysis near our equilibrium point E star. So our starting point will be our singular Hopf point. We'll do a series of coordinate transformations, and we will bring our model to a topological equivalence system that will be valid near the equilibrium point E star. So the new system will be called the normal form, and this normal form, like I said, will be valid only near E star. And this is a relatively simpler system to work with, where again our normal form has three variables, U, V, W. And this is also a slow fast system, with delta being our singular parameter, which is of order square root of epsilon. But now we have one slow variable W and two fast variables U and V. So when we exploit the timescale structure in this system and look at the dynamics of the fast system or the fast subsystem, that is of U and V, it turns out that we can show there exists a surface, which we are calling a quasi-separatic surface, with the property that if we start on one side of the surface, then the system is going to just exhibit small amplitude oscillations. And if you're on the other side of the surface, then we are going to have a large excursion in the phase space. And so anytime a solution crosses the separatic surface, the quasi-separatic surface from the inner to the outer side, then a large spike will be initiated in the system. And this method will be used to determine an early warning signal of a spike. And so to put this into context, here is a time series of X shown here. We have mixed mode transient dynamics, and then we have the asymptotic state over here. We look at the phase space near the fold curve, and we take a suitable section or cross section U equals, which I'm denoting by U equals 0 over here. This blue curve that we see here, that is the intersection of our quasi-separatrix with this Poincare section. And we look at the return points on this section and study their relative positions with respect to this blue curve. Now we put everything again in the normal form variables, and in the normal form, this is how the return points look like. And here we have the threshold in blue, which we are denoting by V alpha star. So if it turns out that if the return points lie above this threshold, then these points will serve as early warning signals of spike in the system. And furthermore, if we have, our normal form analysis gives us a threshold on the slow variable W, which we denote here by dotted line, such that if we are to the left of this threshold, then the system can no longer spike and it will approach the small amplitude limit cycle. So this will then indicate that the system has already experienced a regime shift. So we could find out early warning signals of a spike, as well as detect the regime, and detect the timing of the regime shift by understanding what is happening near the fold curve by doing a normal form analysis. Now let me briefly talk about the second scenario, which when we have a subcritical Hopf bifurcation, and I'll discuss the underlying geometry that supports the bistable behavior. So in this case, our equilibrium point E star is also saddle focus, but now it has a one-dimensional unstable manifold and a two-dimensional stable manifold. So when we approach near E star, we have two possibilities. Either we approach the boundary equilibrium state, which is here, or we approach a periodic attractor, which I've denoted here in magenta. It turns out that there exists some set U, which contains one of the branches of the unstable manifold of E star, which lies in the basin of attraction of this periodic attractor. So if we enter into this set U, then we will be approaching this periodic attractor. And if we fail to enter into this set, then we are going to approach the boundary equilibrium state. And so if we start near this point, the question is, can we detect the long-term behavior of that solution? And secondly, can we also find out early warning signals of extinction of one of the species? And so the idea again here is to again look everything in the normal form variables. So we again transform this and go to our normal form variables. And the normal form, if you look at the dynamics of the fast variable u, then the dynamics of u are characterized by rapid oscillations with slowly varying amplitude. And so we can use this by exploiting this timescale separation, we could average out the fast oscillations and look at the average dynamics or the average system. The average system can be solved nicely. So if you look at the average dynamics of W, it satisfies this equation, which is a linear equation in W bar. So W bar denotes the average dynamics of W. And if we use this form for U, so as I said that we have a slowly varying amplitude with fast oscillations. So we can assume that U has this form. Sorry, I have an incorrect sign here. A is supposed to be positive. So because I have a negative sign here. So we have exponential decay times a sinusoidal function, which is going to represent the dynamics of U. So if we use this form for U, then we could solve for W bar explicitly. And here it turns out that there exists a critical curve, W bar critical, which separates the dynamics of W bar in the following way. So if we are above this critical curve, then W bar is going to attain a global minimum, and then it will approach the periodic attractor. And if we are below W bar critical, then W bar will never attain a minimum, and in this case is going to approach the boundary equilibrium state. And so this can be used to now find early warning signals. So what you do is we again look at the dynamics of U, and we construct a sequence of nested intervals, I0, I1, I2, in the following way. So we'll construct a first interval which contains, let's say, k number of oscillations, where k is some fixed integer greater than or equal to 4. The next interval, I1, will contain k plus 1 oscillations, I2 will contain k plus 2 oscillations, and so on. On each interval, we could compute W bar critical, and then monitor the position of W bar with respect to W bar critical and see what is going on. So this is what I'm trying to explain, what I'm trying to say. So in one case, what we have, so we have these WI criticals drawn over here. And in one case, it turns out that W bar always lies above all these families of critical threshold curves, which would suggest that we are going to approach the periodic attractor. And in the second case, it turns out that W bar is going to cross one of the critical threshold curves, and the point where it crossed will give us an early warning signal of extinction. And now if you put this in context to a time series, so here is where we find our early warning sign at S equals around 28. And this is what it looks like with respect to our original time series. And we note that we could find this early warning signal pretty much in advance, because we do not see any change in the dynamics until S equals 200. And so this will give us access to early intervention if necessary. And so this is how we find early warning signal in scenario 2. And so to summarize, so what we did was we considered a 3-species predator-prey model featuring 2 time scales, and we looked at the dynamics near the singular Hopf bifurcation. We looked at 2 scenarios, scenario 1 where we had a supercritical Hopf bifurcation, and scenario 2 where we had a subcritical Hopf bifurcation. In both cases, we looked at the underlying geometry that supports this kind of behavior. We analyzed the transient dynamics, and we then also found out 2 different methods. One method was used to detect a population spike, and the second method was used to detect a population extinction. So thank you all for listening. I'll be happy to take any questions, and here are some of my references.